Hello, everybody. Welcome to technical session 10 of SIBGRAPI 2021 on segmentation, features, and classification. In this section, we will have 5 presentations. First, for each presentation, a 5-minute pre-recorded presentation will be displayed, and then right after that, the presenter will be online to answer the questions. So I ask the audience to place the questions as early as possible because there is some delay to the YouTube broadcast, and you can post the questions in the YouTube chat or also in the Discord channel of this session. So I think we can now start the presentation. So the first presenter will be the work will be descriptive image gradient from edge-weighted image graph and random forests. And the presenter is Raquel.
Hello everyone, my name is Raquel Almeida and truly grateful for all of you who chose to watch this video. Today I'm going to present our work called Descriptive Image Gradient from Edge-Weighted Image Graph and Random Forest. It's a work that deals with image gradient, which is a transformation process that aims to enhance desirable properties of an image whilst leaving aside noise and non-descriptive characteristics. It's inexpensive to compute and is widely used to assist multiple applications. Here we have some examples of popular gradients like Sobel and Laplace. These methods are kernel methods that have flags good on the edges but is subject to noise. We also present a structure edge detection method proposed by Zoller, Zitnik in 2014, in which the borders are presented as fuzzy borders of the main objects of the image. We argue that borders and contrasting regions are important, but other characteristics that reflect uniformity, homogeneity, and continuity of regions are equally important, particularly for the task of image segmentation. We propose a method called graph-based image gradient (GIG) that's based on edge-weighted graphs aggregated with random forest. This method creates a transformed space that is close to the spatial connectivity of the pixels and reinforced with the relational aspect of the graph. The problem is that the weighting function reflects similarities and responds strong to noises. So, we expect that the random forest attribute selection and implicit regularization could mitigate these problems. Random forests are fast and scalable, but require systematic input like many machine learning algorithms. Here we have a look on the proposed method. From the training image, we transform to grayscale to calculate the graph. On the graph, each vertex represents a pixel, and the edges the similarity between the vertex. To create the regular input of this graph, we take each vertex neighborhood and the neighbors of a neighbors in a vectorial representation. We also add low-level descriptors stored on the vertex. From that, we need to train our random forest using the edge detection task. Because each vertex is associated with a single label, we can work on the discrete space. During testing, we take the regular input subject to the random forest predictions, in which each tree prediction is averaged to create a magnitude value to represent the image gradient. We test and compare our proposed method with other like sets of Laplacian and take all the gradients computed as input to watershed hierarchies for the image segmentation task. Watershed is chosen because its performance depends on the quality of the gradient input. We test and train on the BSDS 500 dataset, testing on the segmentation task and training on the edge detection task. Here we have some examples of the proposed, where we have strong borders, the patterns of the tissue is well represented, as well as the vegetation and the water, creating a good segmentation for large and small objects. The same is not true for SAD, in which the fuzzy borders create a good representation of the large objects, but the small objects and textures are lost. The same for Sobel, which we have great edges, but not represent the patterns and textures, which makes the background take over the main objects of the image. Here we have example where the proposed is not well suited in the case where the input image is presented with high contrast patterns. In this case, we get lost on the small details. The same happens for Sobel, but it's not true for Edge that we can retrieve the main object. In terms of training time, the only two it requires are the gig proposed that takes only 2 minutes to train all 250 trees, while SET take 4 hours to train each of the 8 trees. Inference is similar to all compared methods. Here we have some metrics for the segmentation task, in which the proposed method is superior to all compared. We have also a visualization pairwise comparison that show with statistical significance the superiority of the proposal. So in conclusion, we propose a gradient that highlight boundaries, textures, uniform regions, including shadow. Analysis demonstrate the superiority of the method, and it is also very fast to compute. Further works could involve different hierarchical methods and application as extension to different types of graph. We thank the funding and we thank you for watching.
Okay, let's go to some questions. I can see there is a question by David Menot. So, considering that there are more deep learning based methods with superior effectiveness of yours, and that you have not compared your method with deep learning, how do you think you can extend your approach to surpass the deep learning based ones? Do you have
Yes.
any comments about that?
Yes, I do. In fact, we are preparing a standard version of this paper, which compare the methods. There is no deep learning approach specific for gradient, but there is a lot for edge detection and things like that. And the early previews, the early results we have is that for the comparison of the gradient versus the edges, we still have better results on this final segmentation. If the question is about methods that are specific for segmentation, we are not proposing a segmentation method. So we are doing a comparison with deep learning methods that propose some sort of gradient to create gradient methods. The goal, obvious, future goal of our work is to work with different types of hierarchies like watershed and quasi-flat zones and things like that. So that is the beginning. So we are comparing with deep learning approach for edge detection.
Okay. There is another question from an anonymous reviewer. Could you discuss about the choice for the number of random tree size? I mean, how much trees, and the lack of random feature selection, and how the choice of the attributes affects the results?
Okay, we did research on validation set. We work on BSDS 500 and there is test validation and train. We did a search for the numbers of trees, the user, not for randomized features, how much of these features, also the subsampling of the samples of the input and things like that. And in the end, the difference was less than 5%. And because of the limitation of the size of the paper, we did not discuss this choice of parameter selection, but we did, and there was not, it's only 0.5% from the original results and the final results. So that's why we do not put in the paper.
Okay. I just would like to comment, added maybe a question and a comment, actually. Have you tried or thought about using the image patch instead of computing the graph, the weights? I mean, because you're taking the pixel and its neighbors, right? The edges,
Yes.
as I have understood that by reading the paper. So, have you thought about just taking the raw image region and trying to apply the random forest on that using the pixel
Uh,
as features? Have you tried that or thought?
uh, the use of the pictures, the region, the mask of the features is mostly related to the SED proposal. They create a patch and they represent, but because they work on the structure, the input to relate with the masks of the segmentation, they had all the proposal to make this structure output measure based on the segmentation masks and on the image. The motivation to use a graph is because once you choose one vertex, you can represent the entire neighborhood using just the label of the vertex that you are analyzing. So we create a structure input on the graph to have uh, uh, output that is the label 01 for the dataset. So that's the motivation. But we are working also using, instead of taking the neighborhood like regularly, like a grid in the image, is to take a path that discard all the repeated nodes on the final representation. Like this, I can have a bigger representation, a larger representation of the image around the vertex, and keep the representation compact on the graph. So just discarding the repeated neighborhood.
Okay, thank you.
Thank
So
you.
let's move to the next presentation, I guess. So the second presentation is towards a simple and efficient object-based prefix delineation framework, and it will be presented by Felipe.
Hi there! In this video, I'm going to present our work called Towards a Simple and Efficient Object-Based Superpixel Delineation Framework. This work was made by me, Felipe, and by my colleagues. Now, I'm going to describe all this in more details. Let's use this image as input. The desired object, in this case, is the post sign. The first step selects a number of initial pixels, referred as seeds, significantly higher than the desired quantity of superpixels, that is, an oversampling. After generating the seed set in oversampling, the next step is to generate superpixels through the image foresting transform framework. After generating the superpixels through the IFT, the third step is to remove irrelevant seeds based on the object information. After removing irrelevant seeds, the updated seed set is used for a new execution of the IFT algorithm. This process is performed many times until the desired number of superpixels is finally achieved. In most practical cases, all this requires only 5 iterations, whereas the majority of seed-based approaches performs 10 for any desired superpixel quantity. Now, I'll present our results. Results show that ODIS surpasses all baselines regarding boundary adherence, considering both natural and medical image datasets, while achieves on-par performance in preventing superpixel leakings. In terms of speed, ODIS presents the ability of being faster as the number of superpixels increase. Also, it is not only faster than OISF, but its efficiency can be further improved by recent proposals for the IFT framework. We will now illustrate the ability of ODIS to accurately segment the object of interest using this example image of a helminth egg attached to an impurity. First, we estimate its location. It is possible to see that the resulting map detected the impurity as part of the egg. Using such map as input, ODIS is capable of effectively delineate the object even with such incorrect estimations. If we compare the ODISP result to the baseline, we can see that, as highlighted by the yellow circles, our approach surpasses state-of-the-art methods like LSC and SH in approximating the object borders, while preventing severe leakings often caused by incorrect CLC estimation. For concluding this video, we propose in this video ODISP, a novel object-based method that exploits the benefits of its predecessor for effective object delineation. ODISP is also a faster and more robust approach than other object-based methods. For future work, we are mostly interested in evaluating ODISP for interactive object segmentation. The code of ODISP is publicly available at GitHub. Thanks for watching. If you have any questions, feel free to access my homepage or contact me by email. See ya!
Okay, let's go to some questions, Philip. Let me start with a question. Would be easy to apply this method to the situations where you have multiple objects of interest in the image?
Actually, no. Often CLC maps produce only a binary response. Either it's the object or everything else. So we didn't test, but I think that we might handle it. You proposing a new representation like a multiple object CLC map or multiple object CLC map. So we can. It's kind of straightforward to adapt it for such situation, but we haven't tested it yet.
Okay. We have another question by Moacir. Does the method rely on a salience mask as input along with the image to be segmented? If so, does the competing methods also need it?
I wouldn't say rely, because our proposal kind of extends the another work that is called DISF. So the user may provide, and as we show, it can improve the results. The predecessor, non-object based, already has surpassed many methods, so we kind of take a step further. And most methods, except OISF, do not consider it. So they are limited to, how can I say, they are blind to such possibility that the user might know about the object, like color, and represent it, like sales maps. So it's more like at the same time, it's a pro for our method and a con for the non-object based methods. I hope I had the answer.
Well, that's what you can say later, maybe. So last question. How do you decide when you stop iterating? Actually, I have missed that information.
Yeah. I will try to motivate on why we done this way. Most methods apply 10 iterations anytime. So if they will desires many superpixels or a few, it will apply 10 iterations. So what we have done, by oversampling, and at each iteration, we remove a certain portion of irrelevancy that does not assist in segmentation. We remove the necessity of establishing such number, and it's an exponential curve. So in the first iterations, a lot of seeds are removed, and as the iteration goes, the number that such portion to be removed reduces. And results that we present in this paper show that as the number of superpixels increase, there's no need to apply 10 iterations, and in most practical cases, our number of iterations reduces to 5 without loss of delineation performance. So it kind of it's how can I step? It's a step further now to improve this speed.
Okay, thank you, Felipe. So
Thank you.
I think let's move to the next presentation. So the third paper is new hierarchy-based segmentation layer towards automatic marker proposal, and it will be presented by Gabriel.
Hi, my name is Gabriel Barbosa de Fonseca, and I'm a PhD student at Université Gustavo Eiffel and at PUC Minas, and I will present a work that I've been developing as part of my PhD thesis named New Hierarchy-Based Segmentation Layer towards Automatic Marker Proposal. So, image segmentation can be defined as partitioning an image into different regions of interest, and but performing automatic segmentation sometimes can be difficult. Additionally, the automatic segmentation is also a nilpotent problem by definition, because we cannot know without any type of prior knowledge what is the object of interest for a specific user. So for instance, in the example image that we have here, we can see multiple objects, such as the cat, dog, couch, the pillows, and we also have some objects that are nested within each other. So for instance, the cat's eyes, the necklace that the cat is wearing. So without any prior knowledge, it's not possible to know what is the object of interest for a specific user when going to segment it. And one way to cope with these problems is to add information as the form of user-given markers, so that markers that indicate the location of the object of interest. So the user interaction can improve the segmentation quality, but it is an expensive resource. So studying ways to improve the user interaction by reducing the user's effort is of great interest, and we propose to do that here by automatically proposing markers that a user can either accept as markers that are good enough, or the user could refine to achieve a more satisfactory segmentation. One problem of doing that, automatically proposing markers, in a classical supervised learning way, is that defining optimal markers can be very difficult. So here we have examples of different markers that could lead to the same ideal segmentation, but markers that are different. So defining the optimal ones, it's a complicated task. So our goal here is to then create an end-to-end trainable model that can learn good markers instead of optimal ones. And we define these good markers as markers that can produce a good segmentation when used on a marker-based segmentation method, and that are easily editable by a user. And we make sure that the markers are easily editable by enforcing some desirable shape characteristics on them. So these shape characteristics are, for instance, being small, located near the center of the object, being smooth, and composed by a small number of connected components. And we do that by proposing the following marker learning model. So the marker learning model consists of a marker creation network, which is an encoder-decoder shaped network that takes as input an image plus the object location queue, concatenated one with each other. And the object location queue is basically a small indicator of the location of the object of interest that we want to propose the markers to. And the output of this network is a pair of object and background markers that are maps with the same size of the image containing values between 0 and 1, and with values close to 1 representing the locations of the markers. And during training, we do two main things with these markers. We first use our proposed segmentation layer to compute a segmentation that we can assess with a segmentation loss. And we also propose a set of regularization functions that enforce the shape characteristics that we want on the markers. And a total loss that we want to minimize is composed by the combination of the segmentation loss and the regularization functions. We show that we are able, by using our model, to automatically propose markers that look like human-given markers. So here we have some examples of proposed markers. They are small, they are composed by a small number of connected components, and they are smooth. And when using these proposed markers, we can produce, in general, good segmentations. So some conclusions of this work, some contributions. We generalize a classical segmentation method to the case where markers are fuzzy and make it differentiable to create our segmentation layer that we use on our network. we create the marker learning model using this segmentation layer combined with neural networks. And we show that by using this marker learning model, we can automatically generate markers that are able to recover a good segmentation and have desirable shape characteristics on the training data set and on 4 unseen ones. Thank you very much.
Okay. I have a question, Gabriel. Does this method is the same question actually for the former presentation? Does this method work for producing markers for multiple objects, or it's aimed for just one object in the image?
So for now, as it is right now, our method is only proposing markers for one object. So we consider only a binary segmentation where we have a object and a background. But I think it's possible to extend it to multiple objects. But as our model is, as we are doing right now, it's for only one object appearing in the image. And this is one of the reasons why we use as a part of the input to the network a object location queue, which is a well, should be a simple indicator of the about the location of the object of interest. Because if you have an image with multiple objects, we use this queue to know what is the object that we should propose markers to. But for now, it's only for one object.
Okay. There is a question from an anonymous reviewer, which is with respect to the examples, only results regarding the training dataset are shown. Are the images, oh, it's very specific, shown in figure 4 from the training, validation, or test set of the dataset you have used?
Yes.
Do you remember that?
Yes, to make more clear, the figure 4, it's the qualitative examples. So it's the images that were shown in the presentation. Yes, it's actually we use the MSR810K dataset, which has 10,000 images, and we use 9,000 images for training and 1,000 for validation. So in this case, it's from the dataset that we use for training, but those images are from the validation split. So it's not from the training set that we use. It's from the validation set.
Okay. You could expect this kind of those kind of markers for other data sets also, or have you tried?
Yes. Well, in the paper, unfortunately, we only had space to put the metrics that we computed on the other unseen data sets. But what I can tell you is that we achieve similar markers when testing on the other data sets. The only data set that we have a little bit more problems generating markers is the Pascal-Voc data set, because we train our model in a data set where we have only one object per image. And Pascal-Voc contains multiple objects per image, and some of the objects, they are very small. So sometimes it's a little bit harder to generate markers for these very small objects. But if we, with the exception of Pascal-Voc, for the other data sets that are similar, we have similar results for the markers that are proposed.
Okay. Just the last question. You use a object location queue as an input of the network, and have you tried to change that, and how it is used in your method? It's not clear for me. Could you explain a little bit about that?
Yes, sure. Well, we add the object location queue in the input of the network, because well, one of the things that we claim is that without any type of prior knowledge about the object location, we cannot produce a segmentation for the object if we don't know what is the object of interest for a specific user. And in the same way, we cannot know what is the object of interest to produce markers to if we don't know what is the object that the user is interested in. So our idea is to have in the future, so right now we are using a very strong object location queue, which is the object ground truth, to produce it's more The experiments, they serve as a proof of concept. So there are some beginning experiments. But in the future, we want to have very weak location cues. So for instance, a user could click on the object of interest, and then we propose a set of markers that are more robust and probably produce a better segmentation than the initial object location cue.
Okay. Okay. Thank you, Gabriel.
Thank you.
Let's move to the next presentation. Now we will have domain adaptation for holistic skin detection, and it will be presented by Federico.
Hello everyone, I am Aloysio Dourado and I will present our domain adaptation for holistic skin detection paper. Human skin detection is the task of identifying which pixels of an image respond to the skin. Despite all advances that fully convolutional neural networks have brought for image segmentation, some common criticism is still made to argue that pixel-based approaches are more suitable for skin detection, namely, the need for large training datasets, the specificity or lack of generalization of neural nets, and prediction time. Skin segmentation approaches may be classified into two main groups, local and holistic approaches. Local approaches considers only a small area surrounding the point of interest to classify all the pixels in the image, one by one. In a pixel-based approach, the region that is used to classify each point of the image is a single pixel. Different approaches use different color spaces as input to the classification model. The classification model is usually executed several times to classify all the pixels in the original image. In patch-based approaches, a patch surrounding the pixel of interest is used to classify each point of the image. The main advantage of patch-based over pixel-based approaches is the addition of texture as information for the classification. In holistic approaches, all the image is submitted to an image segmentation model, usually a fully convolutional network, and all the pixels are classified in a single shot by the model. In addition to color and texture, holistic approaches adds contextual information that is expected to improve skin detection. Training data is usually a main concern when using deep learning approaches. There are some existing skin detection datasets. However, each one of them presents a different level of quality, illumination, and other characteristics. Besides that, each dataset presents different kinds of images, general web images, portraits, surveillance cameras, etc. The differences are so relevant that each dataset may be considered as a different domain. Training on a domain and evaluation on another dataset usually leads to poor results due to marginal probability differences of the two domains. However, one may apply domain adaptation methods to reduce undesired effects. In this paper, we evaluate the use of domain adaptation to overcome the data viability problem, using an existing large and diverse dataset to train a network to a domain with few training data. We use a 3-convolutional layer network with max pooling between convolutions and rectified linear unit activation function between inner layers to reduce the vanishing gradient effect. Due to its simplicity and performance, we used UNet as the holistic segmentation method. Our model follows the general original design, but we use a 7-level structure with addition of batch normalization between the convolutional layers. To exploit domain adaptation techniques for the problem of training data viability for skin segmentation, we evaluate 3 domain adaptation techniques. Our last approach consists in combining fine-tune and pseudo-labeling approaches in order to improve the final model performance. The in-domain results clearly show the superiority of data-centric deep learning solutions over traditional color-based approaches. Note that when using compact as source and pratipan as target, the gain of the domain adaptation approach is very expressive when compared to target-only training. Using domain adaptation from compact to SFA leads to impressive results. This observation completely refutes the criticisms of needing large datasets for training and lack of generalization power of deep neural networks. Another important aspect to be addressed is the criticism for the applicability of CNN approach for real-time applications. This is probably valid for patch-based CNN approaches, but it does not hold for our FCN holistic approach. In this work, we refuted some common criticisms regarding the use of deep convolutional networks for skin segmentation. Besides that, we proposed novel approaches for semi-supervised and unsupervised domain application applied to skin segmentation using CNN and evaluated it with an extensive set of experiments. Thank you.
Okay, so I did a mistake. The video was presented by Aloysio, not Fred. So, but I asked to Fred.
Okay.
No question so far, but you did the comparison between the actually among pixel based, pixel classification, then patch classification, and the fully convolutional network. I would like to focus on the last two when you use that sliding window approach to the patch classification. The classification based on patches and the fully convolutional one. And I would like to understand if you try to use larger patches eventually, because I understand that when you use a fully convolutional network, since the depth of the unit is, it has more layers, so the receptive field with respect to each output pixel is larger than the 35 by 35 patch that you used in the sliding window approach. So have you tried larger patches or not?
No, we haven't tried larger patches. The reason we chose a 35 by 35 patch was that the literature that we were using and we were comparing used 32 by 32 patch. It was not the patch base that we used just for comparison, and we really wanted to focus in the holistic approach and in the UNet.
Okay, thank you. There is a question by Moacir. Do you intend to release the code, the model? I guess he's talking about the code of the model, or is it available?
Yeah, the code is available in GitHub. I can type here the repo. I'm not sure if we have the trained model there or just the code for training, but we can let it be available. No problem.
Okay, and another question by Moacir also. It's a question that occurs with recurrently. So, do you think your method will work on different skin tones?
Yeah, we haven't. This is an important matter that we haven't addressed in our work, but I do believe that our approach will work better even with bias in the data sets. Just because looking at holistically, we have more information from the image than the patch or the pixel-based approaches. But this is an important matter that we haven't addressed specifically in this paper, and it's a good reminder for the work.
Yes, I think your idea, your argumentation that there is this holistic view is valid, but you have to test to be sure,
Yeah,
right?
sure. Yeah, for sure.
Because probably the network will see a person and maybe from that detected
Yeah,
skin.
my point is that the UNet approach takes much more information than just the color or even the texture, the local texture of the skin itself. So probably, so I'm guessing here. Of course, there should be experiments to corroborate with what I'm saying. What I guess is that as we have more information than just the pixel color of the skin and or a region that gives us a little bit of texture information, the color of the skin has less importance in this method than in other methods. So that's why I guess that it's better, but I think it's an important matter that we should address in further works.
Okay, thank you. I think we don't have any additional questions, so let's move to the last presentation of this session, a deep learning based approach for tree trunk segmentation, and the work will be presented by Danilo.
Hello everyone, my name is Danilo Jodas. I am a postdoctoral researcher at the São Paulo State University, located in the city of Bauru. And in this video, I'm going to briefly present the overview of our research, which basically combines a deep learning model and image processing algorithm for the segmentation of the tree trunk in street view images of the urban landscape. So nowadays, the main concern of many public administrations around the world involves the urban forest monitoring and the estimation of the tree risk of falling, as the main task is to avoid possible financial losses caused by the damage to the city's infrastructure. So in this sense, we can take the advantage of several technologies that may help the forestry experts to accelerate the tasks related to the tree analysis, including the tree detection and the calculation of measures like the tree height and the diameter of the trunk, for instance, in order to support the evaluation of the tree condition. So considering the automation of the entire process, we can mention the combination of several image modalities with deep learning techniques like convolutional neural networks and image processing algorithm as well. So in this work, we propose the detection of the trunk of the tree in street view images by using a convolutional neural network and image processing techniques to improve the segmentation results. So in summary, we have here the pipeline of the proposed approach, which is basically composed of three steps. The semantic segmentation itself inside the trunk region by using a modified UNet architecture with depth-wise convolutions used to reduce the number of the network parameters. And then the improvement of the results by using an image processing algorithm applied to remove the regions not belonging to the tree trunk. And finally, we perform the extraction of the central line of the trunk by using a simple approach that computes the average points of the left and right boundaries of the segmented region. And the final results can be used in the feature to calculate the trunk diameter and its angle, for instance. And for the training of the model, we have used 8100 images obtained by the cropping of the trunk region, along with the binary masks for the supervised training of the model. And in this figure here illustrates the prototype of the entire process that considers the detection of the holy tree, the trunk, and the crown by a NIOLO model. So you can find more information about the detection approach in our recent publication in the International Journal of Neurosystems. But in short, we detect the tree, the trunk, and the canopy, and then we take the region inside the bounding box of the trunk, represented here in purple color. So it's used as input by our UNet architecture. So that is an overview of what we are proposing in our research. And this process will be used as a supporting tool in order to automatically extract the measures of the tree by using the detected bounding box for further evaluation of its condition, and also the prediction of the risk of falling by machine learning techniques in future works. So thank you for watching.
Okay, Danilo. One question I have is about you mentioned about the diameter of the trunk, but that depends on the scale of the image or the distance the tree. So you don't have information about the depth, right?
No,
So how can you compute that based only on image? Do you have an idea, or is that an issue for you?
No, is that not an issue yet? Because we have an object of reference in the image. It's held by a member of the forestry monitor. So we have an object, in this case, a stick, which has a predefined height, in this case, 3 meters tall. And we use this object for computing the diameter of the trunk, for instance. Okay, so we are trying to use more CNN models for detecting the depth of the pixels, so we can fully automatically calculate this measure in future works. So by now we have to place this object of reference in the sides of the trunk to calculate not the diameter of the trunk, but also the tree trunk, the tree height, and also the diameter of the canopy, for instance. But in our paper, we describe the proposed method. So we have to detect the tree itself, the canopy, and the tree trunk as well. And also we have to detect this object of reference to compute the tree measures. But we are trying to automate this process by maybe calculate the depth of the pixels. Okay.
Okay. I have another question, which is you are computing that center line,
Yes.
and I suppose one of the ideas is to compute the inclination, the angle of the trunk. Maybe the tree is like, I don't know, tilted.
Yes.
So, but that doesn't necessarily mean that there's some danger. And also, there are situations where the tree is straight, but there are other problems. So that won't be. I mean, your method will not be able to detect those situations where the tree is straight in, but maybe I don't know the word in English. Uh, it's rotting inside,
Oh,
so
yes.
you can see from the outside. So there are some limitations. Do you agree with that?
Yes, there is a lot of measures you can take from the tree, and the angle of the tree is one of them. So it's another study performed by forestry and managers. So the tree angle is one of the measures, but also we can use other measures to predict the conditions of the tree. Okay, so we have, for instance, the tree height is one those measures, and along with other measures like we are talking about here by measures seen from images, so internal
Okay.
features is not possible to be taken. So we are analyzing external measures from the images. So basically we have six of them, and the tree height, but the angle of the tree is one of them. Okay, but it's an overview of our research because we are trying to predict the conditions of the tree by only using those measures. I mean external measures and not internal features of the tree. It's
Okay.
the main idea of our research.
Okay. One last question. Do you have some collaboration with governments or some organization to work on that, or you're just trying to measure and see
No,
who,
no, no.
who could use those information?
No. We have a collaboration with the Institute for Technological Research of the University of São Paulo, and there are experts there in urban forestry, urban tree monitoring. So it's a collaboration. It's a multidisciplinary research. Okay, and we are and this measure is based on their work. Okay. But in the literature we can find some which is called dendrometric features from the tree. It's measures calculated from the tree, but the part regarding the analysis of the tree and the measures that are important is from the expert from the Institute for Technological Research. Okay, we are trying to only detect automatically the tree structure and automatically calculate those measures. It's our part of the research.
Okay, thank you, Danilo.
Thank you.
So with this, we finish the 5 presentations. And are there any other questions from the audience? I don't think so. So we have still some minutes, but if there are no questions, we can finish this presentation and move to the closing, perhaps. Okay, I would like to thank you, all the presenters, also the audience, and everybody that is watching this session. And I invite you to continue conversation with the authors at the Discord channel of this session. And also would like to invite you to join the next session in half an hour. It's I think the last session of SIBGRAPI, technical session 11, neural network and classifiers, in 30 minutes. So thank you, everybody.